This last session is the breaking the security of physical devices, and your speaker is Silvio Cesare. Thank you very much.
Thank you. So I am Silvio Cesare. I'm the Director of Anti-Malware Engineering at Kelyess. As said, this talk today is on breaking the security of physical devices. So just a little bit of an introduction. Obviously, there are a lot of electronic systems in the world today. If we look at smart TVs, they've been hacked. If we look at cars, if we look at monitors, laptops, tablets, mobile phones, all of these devices tend to have computer equipment in them. They have microcontrollers. Some even have fully embedded computers inside them. So that is converging. What previously was an electronics world, a hardware world, is now converging into that software/hardware computing arena. So IT security techniques can be used to look at the security of these devices. And that's pretty much what I set out to do with this particular research. I wanted to look at devices that were commonly found in the home or that were easily accessible to me and investigate the security properties of those devices. So specifically what I'm going to talk about today, there are 4 things. I'm going to be talking about eavesdropping on analog baby monitors. Analog baby monitors are still available, they're still quite popular, but you look at you're starting to see digital and IP-based baby monitors take over now. But analog versions are still available. You can buy them on eBay and buy them brand new. I've bought some from markets as well. I'll be looking at disabling RF-based home alarm systems, looking at popular home alarm systems that you can buy from depot stores and home hardware shops. I'll be looking at hardware tampering with one of those home alarms and seeing what can be done there. And then finally, I'll talk about defeating the keyless entry of a 2000 to 2005 model car. I know it's an old car, but I think it's an illustrating example of the security of these types of devices. So I'll start off with eavesdropping on analog baby monitors. Like I said, analog baby monitors are the older style of system. You start to see even video monitors today and IP-based. And I think there have been some reports in the past year or so, past 1 or 2 years, about people hacking the IP-based baby monitors through insecure Wi-Fi. The ones that I'm looking at today are the analog, the radio-based ones. You can buy them off eBay, other places, quite reasonably priced. So given that we're looking at an analog system, the obvious sort of thing that we're thinking about is it a radio broadcast? Is it radio transmissions? Is it AM? Is it FM? And what can we use to analyze these radio signals if in fact it is radio? And that brings us to software-defined radio. It's a perfect use for analyzing this particular type of system. You can get a variety of software-defined radios from the very low end, from the TV tuner software-defined radio dongles. They're about $15. And that's receive only, so you can't actually transmit on those devices. Another type of device is a FunCube dongle Pro, I think they're being sold as. And this is similar to a TV tuner dongle, I think slightly more bandwidth, slightly more expensive as well, but it's in that category of receive only. And it has a similar frequency span as well. You also need some antennas. You can get antennas off eBay, they're quite cheap, some omnidirectional ones and so forth. On the left of on the slide here is a picture of a little TV tuner software-defined radio, and on the top right is the FunCube dongle, and obviously there are some antennas there as well. So the thing about these types of software-defined radios, they tend to have a frequency span that can be processed, and the bottom end of these devices is around 64 megahertz, give or take. So a lot of the TV tuner dongles start at about 64 megahertz, and the thing is, analog baby monitors probably are going to be using the lower end of the spectrum. They're probably going to be below 64 megahertz. There's some allocations in the frequency planning that you'd expect that they would be in that range. So the way that you can look at these frequencies in the low end of the spectrum is to use up converters. And I've got a picture of a hammered up converter in the slide. An up converter basically takes a lower frequency and moves it into in the spectrum to a higher frequency that can be analysed by your typical software-defined radio. So the hammered up converter I've got here works on the HF and MF bands and then moves it up into the spectrum. So it can take a 30 megahertz, a 40 megahertz, a 50 megahertz signal and move it up into somewhere around 125 megahertz plus, which can be processed by your TV tuner software-defined radio. So the ambient converter is quite cheap as well. So it's not as cheap as the software-defined radios, the TV tuner ones, but it's in that affordable price bracket that if you want to investigate it, you certainly can do it. So we've got a potentially an analog signal that's being transmitted by this baby monitor. That's the theory. So how do we find exactly, if at all, and if it is, and what frequency is being transmitted by this baby monitor? So one way of doing this is by using a spectrum analyzer or using spectrum analysis. A spectrum analyzer basically takes a large band of frequencies and then tells you what the power level on various bands are. So you can identify signals being transmitted at particular frequencies using a spectrum analyzer. There are high-end spectrum analyzers and there's low-end spectrum analyzers. A high-end spectrum analyzer is a very expensive piece of kit. You could, from thousands to tens of thousands of dollars. Probably some of the devices that are making this more affordable now are things like the RF Explorer, which I've shown on the right, and that's for maybe about $300, I think you can get that today. And if you just want to find what signals, what frequencies are in use in your area, then you can use this type of device. If you want to do other types of processing, maybe you need the high-end spectrum analyzer tools. But if you just want to find what signals, what frequencies are in use and being transmitted on, this type of spectrum analyzer is quite good. And what I found when I was looking at these baby monitors, 40 megahertz, there was a spike in the signal for the spectrum analyzer. So we can see something is being transmitted by the baby monitor in its room at 40 megahertz. And we presume that's an analog signal. So we assume that it's some sort of radio transmission, it's an analog transmission. How do we turn that transmission into some audio so we can hear actually what's being transmitted from this baby monitor? At this point, we can use software spectrum analysis tools. On Linux, you have GQRX, and on Windows, you have HDSDR. GQRX is actually based on GNU Radio, so it's quite good. And they're very similar, GQRX and HDSDR. You pretty much just run the software, you have your TV tuner software-defined radio in it, and then you select your specific frequency. We know that it's at 40 megahertz. And then we try different demodulation schemes, AM, FM. And what we can find with this particular baby monitor, there's an AM transmission at 40 megahertz that has audio on it. And the transmission is actually being transmitted continuously. So typically for baby monitors, once the volume reaches a certain point, then you hear something in another room. But in fact, the baby monitors are continuously transmitting, and it's up to the receiver to determine what the threshold is for making the sounds audible. So that's a pretty sort of simple introduction to how you can use software-defined radio to listen into a radio station, and that radio station being an analog baby monitor. What types of things can you mitigate against people listening from outside your house with a software-defined radio and an antenna? We can use digital baby monitors. There's things like DECT, and DECT is the digital standard that your cordless phone probably uses. Yes, I know DECT has been broken, but the attacks aren't widely implemented or used. You can also use IP-based solutions, and this is probably the way to go, but you have to make sure that your IP-based baby monitor is secure as well, because as I said earlier, there have been attacks. Malicious people have interfered with the IP-based baby monitors. So the next thing that I want to talk about is disabling RF-based home alarm systems. And I've got a picture here of a typical stock photo of a home alarm system. It has a key fob, and the key fob communicates wirelessly to the receiver or the base station. It has a motion sensor as well. What home alarms use these types of key fobs or remotes to disable and enable the alarm system? Pretty much all of them, heaps in fact. Almost everything at Home Depot and hardware stores use these types of systems. In Australia, we have our sort of department stores such as Big W, and I know the US has Kmart as well. And we have Bunnings, which is our sort of our home hardware chain, our major one. All of these systems use these key fobs that enable and disable the alarm system. As you're coming in through your driveway when you're going home, you just disable the system and you go into your home. And here's an example. I think I've shown this here in the slides. This system cost about $110. That's sort of towards the upper end of the home alarm market. It's not a commercial grade system, but for a home alarm system, it's one of the upper end ones. So the funny thing is about that these home alarm systems, the way they work, these key fobs, is that they send a fixed code to the base station. When you press disable or enable on your remote, they're sending the same code every time you press that button. And what that means is that these systems are susceptible to replay attacks. A replay attack simply captures the code that's being transmitted and replays it. And it works because the same code is used every single time you press the button. So you're simply cloning the remote by capturing that wireless transmission. So in an attack scenario, the real remote, the homeowner, when he's coming in one night, disables the alarm system, and an attacker, maybe next door with an antenna and a software-defined radio, is listening and recording that transmission. And then later, when the homeowner has left for the evening and turned on enabled the alarm system, the attacker replays that captured code and disables the system. And this works on almost all home alarms, pretty much everything that I tested. I doubt it will work on commercial systems because there are other techniques that can be used to prevent these types of fixed code replay attacks. The alarm key fobs generally use 315 megahertz and 433.92 megahertz. These are the typically allocated frequencies for these types of key fobs. You need different hardware to do this type of attack than the analog baby monitor attack. You need a software-defined radio that can transmit as well as receive. There are some new software-defined radios that have been appearing and coming out. Probably one of the sort of more well-known ones is the HackRF, which should be available to use now or very shortly. And this is sort of the low end, I think it's about $300-400 they're selling them at now. What I've pictured here and what I used was the USRP B200. The B200 is sort of the new USRP. The B200 is the low-end model as well. It costs about $1,000 to get this particular USRP, and it's different from the older USRPs, the N series and whatnot. You don't have to put daughter boards into the device, and it's powered by USB, and it has external power as well if you want it, but you don't have to use it. It also, as previous slides, you have to use antennas to do the receiving and transmitting. And these are again off eBay quite cheaply. So how do you implement a replay attack? You know, we've got the hardware, which is the USRP, or maybe a HackRF if anyone has one. You can use GNU Radio. GNU Radio is a software kit to do workflows and visualization of software-defined radio. It really makes this all possible. To implement it, you basically join blocks together and you come up with a workflow and then run that. So to capture a signal, to capture the home alarm key fob transmitting disable, you simply set a source block as a USRP and then a sync as a file. So you're dumping data received in the USRP to a file. And to replay it, you simply set a source as a file and a sync as a USRP. So within about 4 blocks, you can implement a replay attack in GNU Radio. So, you know, I'm talking about a very sort of high level of what, you know, capturing an RF signal and replaying it. But what is actually in the RF signal? Generally, these RF signals at these particular frequencies with key fobs are modulated with amplitude modulation and pulse width modulation. If we demodulate that RF signal, we can actually see if the remote that's being used, if the code is a fixed code or a rolling code. And we can do that with GNU Radio and custom software. So to explain a little bit about amplitude modulation, I know this is, for people that know software-defined radio, I suppose it's quite introductory, but for people that don't, it gives a good idea of what it is. You start off with a carrier signal, that's at 315 megahertz or 433.92 megahertz. And then you have, in the diagram I think I've shown here, is a modulating sine wave signal. That's your baseband signal, the data that you're transmitting. So you simply modify the amplitude of the carrier signal to be that of the baseband signal. And your final result is a modulated transmission. The envelope of that modulated signal is your baseband. So often we're not putting analog data across a transmission. Typically we're not for this type of stuff. We're putting a digital signal. And often we just use amplitude modulation in terms of whether it's on and whether it's off. So we simply modulate the carrier wave, and then we don't modulate it. But sometimes, a lot of times, we also use pulse width modulation. So we leave the modulated signal on for a specific amount of time, and the length of that time indicates what type of symbol it is. So in the diagram that I've shown here, we've got some wide pulse widths. That represents a 1 in this case, and we've got some short pulse widths, and that represents a 0. So that's pulse width modulation. When you're demodulating an unknown signal, you don't really know what the widths of these pulses are, but you know that there are wide pulses and there are short pulses. So how do you know how wide is a wide pulse and how short is a short pulse? I use some clustering software, Pi Cluster in particular, and I group similar widths together. So that groups all the wide pulses together and all the short pulses together using cluster software. And then I found the mean of each of those clusters. So there are 2 clusters, the wide and the short pulses. I found the mean of those clusters, and then I found the mean of those means. So that gave me a threshold to indicate whether a pulse was either wide or whether it was short. And that enabled me to determine the symbols, whether they were a 1 or a 0. So you can do this type of attack with a USRP. But really, you don't need this extensive hardware if you're simply focusing on AM and pulse width modulation. You can implement this with some electronics for about $50 and an Arduino using a wireless AM transmitter and receiver module. And you can buy these modules from various places. Most of your consumer, like your home, your hobbyist electronics stores will have this type of equipment. And then the thing with these module pairs, they simply demodulate the signal that's coming in from an antenna. A lot of them don't even need antennas, they have an inbuilt antenna. And then you can use that to power an Arduino, and you figure out the data from that. So how do you mitigate against these types of attacks on home alarm systems that key fobs are using fixed codes that we can replay and disable the system? Well, what we can use are rolling codes or challenge response system. A rolling code system is a code that when you press the key fob, every time you press it, it changes what's being sent. And the way that this works is you have a key fob and you have your receiver, and they both have a pseudo-random number generator, the same algorithm on both, and they're synchronized so that they can expect, but so that they know what the pseudo-random number generator on the other component is. So the key fob gets the next random number from its random number generator, pseudo-random number generator, and transmits it. And the receiver, knowing the state of the pseudo-random number generator, knows the next number in that sequence. And if it's the same, then it believes it's been authenticated. I'll talk a little bit more about rolling codes in the keyless entry work, and you'll see some attacks on that. Other things to mitigate the home alarm attacks by commercial alarm systems. I mean, I think there is going to be a really big difference between your home grade and your commercial grade alarm systems. You would expect that commercial grade systems don't use fixed codes because the security is so poor. And avoid those Home Depot, those home hardware stores that sell for that home market if you're concerned about security. The next thing I want to talk about is hardware tampering with an alarm system. So back to a shop at our home hardware store. I think I showed this earlier, it's about $110, a home alarm system, a home wireless alarm system with a keypad controller, some motion sensors, and some key fobs. So I took off the case of the receiver, the controller with the keypad, and what I saw was there was one major IC that was labeled, and there were also some test points, some test pads, some test ports. I soldered some header pins onto those test ports, and the labeled IC indicated that it was a PIC microcontroller. Now, PIC microcontrollers have an in-circuit programming interface that can be used for debugging and programming. So I had this assumption maybe maybe this PIC microcontroller has these test ports allocated just for that purpose. If you look at the pinout for this interface, you can see that the ground pin is at a very specific location. It's the third pin from the top in this diagram. So we can use a continuity test with our multimeter to determine which, if any, of those test ports are ground. And in fact, we do find that the third pin from one direction is ground. So it's starting to look like it might be this interface. I've attached a PIC device programmer, in this case a Picket3, which is a pretty popular device programmer for PIC microcontrollers. And yes, I can actually recognize the microcontroller. Typically you can do things like read the firmware, write to data, write firmware, get the status information, get configuration information from the microcontroller. The PIC microcontrollers, at least some of them, do have a security feature that if a fuse is set, you can no longer read firmware from the device. You can reprogram it, but you have to erase it first. And in fact, this home alarm system did have this fuse set, so you couldn't actually read the firmware off the device. However, the data was readable. And what was in this data was the keypad secret passcode to disable and enable the alarm. So how would we get the firmware off the device, off the microcontroller, if we really wanted to? And I think this is something that I want to work on going forward. There are a couple of types of attacks that we can do. Glitching is one of them, and glitching is basically introducing faults into a system, and typical ways of introducing faults are by modifying the voltage or a clock signal. And the idea behind this is if we modify the clock signal at a particular location, we can possibly modify code or data on the microcontroller. And if we get to the point where we're checking for that security fuse to say, can this firmware be read? If we glitch it at that point, it's conceivable that we may pass that security check. Some other approaches include decapping the IC and changing the security fuse with UV light. Decapping or decapsulation is removing the epoxy packaging from the package and revealing the silicon die beneath. If we reveal the silicon, we may be able to change that security fuse using UV light, providing we mask off areas of the silicon that we don't want to modify. And you typically use things like acids and chemistry to do this, as I've shown in the pictures. So how do we mitigate against these types of attacks? If we can read the passcode, if we can change the passcode on the devices, we do need physical access, but should we mitigate against this? Don't label the ICs. It's a very simple technique. But if we don't label the ICs, it does make it harder for an attacker to realize what component this is. And if it's a commercial off-the-shelf component, we can simply look up we can look up information on it. We know what things we can do to attack it. We also have to assume that there are going to be hardware hackers and people attacking the hardware, but it is hard to stop a well-resourced attacker. Well-resourced attackers are using focused ion beams, they're using X-rays, they're using full chemistry kits. It is very hard to stop. So finally, the final sort of component of this talk is defeating the keyless entry of a 2000 to 2005 model car. I've shown stock footage of the particular car in question, but I'll show some more photos later on. Why a 2000 to 2005 model car? Well, this is what I owned. Well, actually, my girlfriend owned this car, and so I had access to this car. Apparently, it's still being sold in Malaysia and still being built in Malaysia. It is a popular car, especially where I'm from. I know America has a version of it as well. On my street at home, I can see my neighbours have two cars of the same model. So it's certainly something that I had access to. So the first thing that I really needed to do was build a data set. I'm talking about capturing codes from the remote. I wanted a data set of codes that were being sent by the key fob, so I could look at them, so I could see if there were any cryptographic weaknesses, so I could see if it was a fixed code or a rolling code. I've actually got so this is the This is the button pushing robot that I built. It's sort of over-engineered, I know, but there is valid reasoning for this. It's basically an Arduino powered solenoid, has a relay. You can adjust the speed. I mean, there is reasoning for doing it like this. You know, people ask me often, you know, why didn't you just, you know, take apart the key fob and solder some wires and use a relay or something to that effect? And then, you know, I don't want to destroy the key fob. I want to be able to take a key fob of my neighbour's, you know, put it into this little device, you know, and get a good data set of button pushers. So it's powered by a little power supply as well for the solenoid, and it has a relay that gives it power. So if we analyse the rolling code, we've got like a large data set of button pushers now, and it's all using amplitude modulation and pulse width modulation. So we've used that same code and same techniques from home alarm systems into the keyless entry of this car, the same demodulation of that. And if we look at the codes that we get out of that, we can see that there's some patterns. Each code consists of a preamble, and that's based on the remote identification, the actual key fob identification. And that's because there's a pairing between the car and the key fob, that the key fob has to have an ID. That's followed by a few bits that specify what type of function the key fob is doing, whether it's locking the car, whether it's unlocking the car, whether it's causing a panic, or whether it's opening the trunk. And then after that, there's about 16 to 17 bits of the actual rolling code, the part that changes each time, and that's the security mechanism. It's not really a bit, though. It actually consists of 3 states. I'll just say bit. Each bit can either be a 1, a 0, or a gap. A gap is simply silence in the transmission. And gaps, strangely enough, are actually quite important. If you remove some of the gaps between the 1s and the 0s, it doesn't actually work. For timing, a 1 is twice the pulse width as a 0, and there's an implicit gap after every 1 or 0. A gap is the width of a 0 as well. So about 10 or so years ago, maybe 12 or 13 years ago now, there were some attacks by Michael Zalewski. He wrote a couple of papers, one paper in particular about strange attractors, where he visualized the initial sequence numbers in 3 dimensions and was able to use that visualization to find non-uniformity in the pseudo-random number generators that were being used. The way that he did that was basically taking a sequence of numbers, or a sequence of initial sequence numbers, and taking the difference between each number, and then he used that difference to represent a particular axis in 3-dimensional space. So it would be X, and then the next one would be Y, and the next one would be Z. Now the thing is, in a perfectly uniform pseudo-random number generator, I'm probably using the wrong terminology, but in a perfectly uniform pseudo-random number generator, a perfectly random pseudo-random number generator, you would expect a uniform distribution of points in this space. But in fact, what Michael Zalewski found was that some TCP stacks had non-uniformity, and there was actually patterns emerging, and he could exploit this non-uniformity to predict sequence numbers based on previous sequence numbers. So I've actually shown 2 plots from 2 cars. The one on the left is the car I'm actually attacking in this talk, and the one on the right is another type of car. The one on the right is actually more secure than the one on the left, simply for the fact that it's much more dispersed, even though you can see that there's some non-uniformity there. But the one on the left shows it's a very dense collection of points, and there's actually not much difference between successive numbers in this rolling code. So using software that is available, that Michael Zalewski wrote 12 years ago to predict sequence numbers, you simply capture 3 codes from the remote, the car remote, use that software to predict the next rolling code. In simulation, it works great. And it does work, but I want to discuss a few other things as well before I get into that. When we go to actually transmitting the rolling code, we can increase the range of our transmission by using an amplifier. I've shown a low noise amplifier in this diagram here. It's by mini circuits. It has a pretty good gain and it has quite low noise. It's also powered by a power supply, of course. So before I get into saying, it did work, and there's some other attacks that I'll talk about soon, but in this particular attack, it did work. But how do we actually test, one code is being correctly received by the car? Because, you don't want to perform an attack and you think to yourself, oh, in simulation it works perfectly, but the car's not reading it correctly. What have I done wrong? So the way to do this is to do a capture and replay the codes in a confined environment. So we're capturing the code sent by the remote and stopping it being transmitted to the car, and then we're replaying it using our demodulation and modulation system to verify that the code we're sending to the car is correctly processed. So how do we stop the car from receiving the codes? Well, the normal thing to do is to use a Faraday cage. A Faraday cage is a cage that has a conductive exterior, and RF can't really penetrate to inside or outside of the cage. You don't always have to use a solid conductive cage. You can use a mesh, and the size of the mesh determines what frequencies can penetrate the RF, can penetrate the cage. But in fact, it's even on Wikipedia that thieves in other countries, when they're trying to steal something from a store and get through the scanners without the scanners going off, they'll just stick an object into a freezer bag, and the scanners won't be able to scan the object in the freezer bag because the freezer bag acts as a Faraday cage. It's an aluminium foil lined bag. It has that conductive exterior, and in fact in this, what I actually used was use two freezer bags together because I think some of the seams let some RF out as well. So, I mean, that's one attack, predicting the next code based on the previous codes. But I think there's cooler attacks out there. I don't like the fact that you have to listen to 3 codes. It's not very realistic. So it would be nice to have, a more practical attack. So we'll just analyze these codes that are being sent a little bit more. The entire rolling code sequence has a fixed time. So all the ones and zeros and the gaps sum to a fixed number. So that's one constraint that we can think of. There are fewer X's or gaps than ones and zeros. And an X or a gap never follows another gap. So if we capture one transmission to get that preamble of the remote, we can brute force the rolling code part. We generate all numbers in that range. Remember, that's about 16 to 17 bits, and there's 3 states per bit. And we have those constraints, such as there are a certain number of ones and zeros and certain timing constraints. And we can actually get that to about fewer than 1 million possibilities of that rolling code section. Does it work? Yes. It generally unlocks the car in under 2 hours. Generally under an hour, to be honest. And sometimes as fast as a minute. I've got actually a video of this. So this is the car that I have in my garage. The first thing that I do, of course, is to lock the car. So locking the car with the key fob, just testing to see if it opens. Obviously it doesn't. The test lab at home got power supplies, function generators, USRP, various things like that. A messy desk. And we're transmitting the codes now. So each one of those green bars is a transmission of a code. And a minute later, car unlocks. Now, I'm not aware that it's unlocked at this point. I'm just, I'm thinking to myself, I'm in my room, in the house. Not aware of what's going on in the car. I'm thinking I need to give it some time to brute force through the codes. But it's still sending the code. So after 4 minutes, it's found another successful code and unlocked it again. So eventually I come out. I think it's after about 15 minutes, I've decided I may as well check the car to see if it's unlocked. Then it's unlocked. Now, an interesting thing is, though, that when I've been testing the brute force component of the hack, I've noticed that at a certain duration, the car has seemed to unlock at the same time for quite a few times. So I'm thinking, well, this is little coincidental. So what I've found out is that some codes always unlock the car, and it seems to avoid the rolling code security. So we have a fixed code that is unlocking the car each time, and once known, unlocking the car takes seconds, not minutes or hours. It does appear to be a manufacturer backdoor, but I should add a caveat here. After about a week or two, the backdoor stopped working. So is it a time-based backdoor? It's hard to say. It does appear, though, that there is a manufacturer backdoor of some sorts, and the backdoor is tied to the remote. So it's not a generic backdoor that works every single time in every car. You've got to know the preamble of the code, of the code that's being sent by the remote for the backdoor to work. So it's tied with the remote as well. So how do you mitigate against these types of things? Well, it's hard to mitigate this type of problem without a recall. And to be honest, a recall is never going to happen. You could, of course, install an aftermarket keyless entry system or possibly just upgrade your car. I do believe the security of cars has improved significantly over time. But if you're a car maker as well, don't use an algorithm to generate the rolling code, or at least employ cryptographers to do this work. Don't put in backdoors is another obvious thing, because once known, obviously, it's a field day for thieves. Another thing that is a very sort of useful thing that could be done is simply provide a lockout after a certain number of failed attempts. I mean, I've sent thousands of codes, tens of thousands of codes to the car, and it hasn't locked me out, or at least imposed a time delay on me. So after 20 failed attempts, a lockout of 60 seconds could be quite reasonable, and I think that would significantly reduce the possibility or the feasibility of performing a brute force attack. In the future, I'd like to do silicon analysis of the IC in the key fob and the receiver. I've actually, a person was in contact with me and was able to identify this particular microcontroller that was used in the key fob. And if you look at the key fob, it's a particular type of IC that is amenable to silicon level analysis, where you decap the IC, you take some visualizations of it, and you can extract the firmware and code from that imagery. So it seems quite conceivable at this point that I could get the firmware off the device. If I get the firmware off the device, I'll be able to know for sure what exactly these backdoors are, what algorithms are being used to generate these pseudo-random numbers. And that is really where I want to go to, get into that firmware recovery stage. And that's a thing that I'm working on currently, and hopefully in a few months I'll have that going. So that's pretty much the talk. Hardware hacking is fun. I mean, it's an enjoyable thing to do, and I think a lot of software people are able to do things in hardware today that would have required an engineering degree many years ago. Lots of real-world devices are vulnerable, and if you look at rolling codes in implementations, they've been largely uninvestigated. There's not a lot of pseudo-random number generators out there that have been investigated in terms of rolling codes. Keylock was a system that was broken some time ago, and that's probably the most well-known attack on keyless entry systems. So that concludes my presentation. Are there any questions?
You mentioned that you had two neighbors who also had the same model car. Did you manage to unlock by accident their car too during this experiment?
The thing is the unlock code is tied to the remote as well. So if I eavesdropped on their remote and captured their code, then it's quite conceivable that I could unlock their car. However, I thought if I start to eavesdrop on my neighbor's car, it's probably crossing the line of best practice there.
Thank you.
When you were testing transmission of the key codes while preventing the car from receiving them, did you ever run into issues with desynchronization of the keys with the actual receiver in the car?
Okay, so that was a good question actually about the desynchronization. So when you do the brute forcing, it desynchronizes slightly. So typically what happens is for the next 2 to 3 or 4 button pushes, the remote doesn't work. And then at that point it synchronizes up again. Because we talked about earlier that there are 2 pseudo-random number generators that are in synchronization with each other. And the pseudo-random number generator on the receiver typically has a window of acceptable codes, simply for the fact that if the key fob is pressed 5 times without the car being around, then they'll desynchronize, and if it doesn't have that window of opportunity to accept codes, then it will simply lock out that key fob. So there is a desynchronization that occurs, but I've never completely desynchronized the remote to the car. It's typically been about 2 to 4 button pushes that have been out of sync.
Okay, yeah, it's my understanding there's frequently manufacturer mechanisms to resynchronize, like getting in the car and physically, holding some buttons down to resynchronize them. I was wondering if you'd ever had to do that.
There is a programming procedure, and it looks like there's security problems in the programming procedure. I mean, the way that it's orchestrated, to me, it can't be secure, the way that a remote is paired with the car. So there has to be security problems there. But they're typically for cars, you do have a procedure for syncing a remote to a car. I've bought some off for this particular car as well off eBay, and then done the programming procedure to test the backdoor if it's present in other remotes. But it's specific to the remote ID as well.
Thank you.
It seems like most of the attacks that used on the devices, homes, or cars required a lot of effort and time in order to actually break that single device. What would kind of scare me is if the information you gathered was able to just attack now any home, any car, any device. So 3 hours to do one home is scary, but not super scary. But if 3 hours now you can attack any home or any device, that's what would terrify me. I'm just curious if you found anything that would let you quickly attack another home or device.
I think if an attacker wants to get into a house, a brick or a kick in the door is probably the way to go if they want to get in really quickly. But I mean, I don't think that the attacks that I looked at specifically, where I suppose the car attack was specific to the manufacturer of the car. Now, I presume there are going to be other implementations of the rolling code and keyless entry that are used on other cars and other makes, because typically what happens is that a manufacturer of this particular security device or rolling code implementation resells it or licenses it out to car makers. So you would assume that there are other cars that are vulnerable out there. I don't know the extent of what that is because I haven't been able to establish who the people that are buying this keyless entry system are. In terms of the home alarm systems, I think it's fairly feasible that a replay attack would work on most home alarm systems that are out there that use this type of technology. You can certainly listen in at 315 megahertz or 433.92 megahertz and just capture everything. And then you probably will be able to get into most home alarms. There is going to be that time delay though, because you have to wait until a person comes home and disables the system, and you probably have to set up a listening device outside the house as well. It seems to be like a large amount of effort for typical attackers, but certainly these types of things are feasible.
Thank you.
Thank you very much.